Section: Introduction. In this section, we discuss how sparsely activated MoE transformers outperform dense models that require the same amount of floating point operations during inference. This advantage is crucial in the current landscape of foundation models, which primarily spend their time being used for inference. As a result, many language models, both open source and closed source, have adopted the MoE architecture. Given the benefits of MoEs, we recognize that practitioners will want to update these models with new data, similar to how dense transformers are updated. We note that continual pre-training, which involves techniques like replay, learning rate rewarming, and redecaying, has proven effective for dense autoregressive transformers. This approach is competitive with full retraining but is more cost-effective. However, we question whether these same strategies will work for continually pre-training MoE large language models, LLMs. We acknowledge that MoE pre-training can be challenging due to instabilities from the routing algorithm and the need to balance the load across different experts. These issues may worsen during continual pre-training, especially with shifts in data distribution. If not managed properly, MoE transformers may develop inefficient routing strategies that overuse certain experts, resulting in decreased performance and poor resource utilization. While load balancing strategies are employed to mitigate these issues, the algorithms used in state-of-the-art MoEs were not specifically designed for the non-IID data distributions encountered during continual pre-training. Adjusting the router's decisions to accommodate new distributions could disrupt the balance established with previous data, leading to increased forgetting and inefficient resource use. To address these challenges, we conduct a systematic study of MoE continual pre-training. We select two popular routing algorithms and two well-known MoE architectures, resulting in 4 different MoEs for our analysis. We pre-train each MoE language model on a substantial dataset and then continually pre-train them on additional data from different sources. Our contributions include establishing the impact of replay and infinite learning rate schedules on the dynamics of forgetting and routing imbalance during continual pre-training. We demonstrate that a penalty-balanced MoE can match the performance of a full retraining baseline at a lower cost. We find that both penalty-balanced and Sinkhorn-balanced routing algorithms are robust against distribution shifts in terms of language modeling performance and routing imbalance. Additionally, we provide a detailed analysis of how routing decisions evolve during continual pre-training, offering insights into how MoEs adapt to new data while managing previous knowledge. We also explain that continual pre-training involves training models on a series of large datasets with different distributions, which distinguishes it from smaller-scale supervised fine-tuning. We highlight established techniques for continual pre-training dense transformers, such as learning rate rewarming and redecaying, which are essential for effective adaptation. We discuss the importance of infinite learning rate schedules to avoid forgetting and the role of replaying previous data to mitigate catastrophic forgetting during continual pre-training. Section Summary. In this section, we discuss the advantages of sparsely activated MoE transformers over dense models, particularly in continual pre-training, and highlight the challenges of maintaining load balance and routing stability during this process. We also outline our systematic study on MoE continual pre-training, examining various routing algorithms and architectures, and demonstrate that specific strategies can effectively mitigate forgetting and performance degradation while adapting to new data distributions. Section: Mixture of Experts Transformer Language Models. In this section, we discuss mixture of experts, MoE, transformer language models. Unlike traditional dense transformers, sparsely activated MoE transformers dynamically direct tokens in a sequence to various experts instead of just one. Here, the sequence length refers to the number of tokens, the hidden dimension is the size of the transformer's internal representation, and we have multiple experts within each transformer block. We typically replace feed-forward networks, FFNs, in each block with MoE layers, and recent studies have also integrated MoE layers into the query and output matrices of multi-head self-attention layers. Our focus is on MoE transformers that substitute FFNs with MoE layers, similar to cutting-edge research. We also explore the trend of using more specialized and shared experts. Central to MoEs are routing algorithms that determine how tokens are assigned to experts. A crucial aspect of these algorithms is maintaining a balanced load across experts to avoid overloading a few, which can lead to inefficient parameter use and increased latency. We concentrate on two leading routing algorithms: penalty balanced top-1 routing, PBT1, and Synchron balanced top-1 routing, SBT1. Both algorithms utilize a straightforward linear projection to determine expert probabilities, which are calculated using a softmax function. The top expert is selected for each token based on these probabilities. For a single token, the output of the MoE layer is computed based on the top elements and may involve a shared expert if applicable. While both routing methods aim to select the top expert, they differ in their approach to balancing the load. In PBT1 routing, penalty terms are added to the overall loss to encourage a balanced distribution of tokens among experts. The auxiliary loss, which promotes equal token assignment, is commonly used alongside the Z-loss, which helps maintain numerical stability in larger models. We focus on MoEs that incorporate both losses, referring to them as PBT1 MoEs. On the other hand, SBT1 routing frames the token assignment as a linear assignment problem, which is a well-known issue in optimal transport. The Synchron algorithm offers an efficient solution to this problem, allowing us to adjust routing probabilities to achieve a balanced load while still following a greedy selection of the top expert. In the related work section, we review literature pertinent to our study, with a more detailed discussion available in the appendix. We also examine continual pre-training of dense foundation models, noting that self-supervised pre-training can reduce forgetting. Research indicates that pre-trained models retain information better than those initialized randomly, and larger, wider models tend to forget less than deeper ones. In the context of large-scale continual pre-training of language models, we emphasize the importance of rewarming the learning rate when starting from a checkpoint with a low learning rate. Following previous studies, we confirm the effectiveness of learning rate rewarming, redecaying, and replay in this process. Section Summary. In this section, we explore mixture of experts, MoE, transformers, which dynamically route tokens to different experts instead of a single feed-forward network, focusing on two routing algorithms: penalty balanced top-1, PBT1, and Synchron balanced top-1, SBT1, each designed to ensure balanced load across experts. We also review related literature on continual pre-training of dense foundation models, emphasizing the benefits of self-supervised pre-training and strategies like learning rate rewarming to mitigate forgetting in large-scale models. Section: Continual Pre-training of MoE LLMs. In this section, we explore the continual pre-training of mixture of experts, MoE, large language models, LLMs. To our knowledge, there is only one study that examines large-scale continual pre-training of MoE LLMs, while most research focuses on enhancing or expanding MoEs for this purpose. A recent preprint, DeepSeek Coder v2, demonstrates the ability to continue training a MoE LLM from a checkpoint, but this is only shown in one case, and it does not analyze the MoE routing behavior. Additionally, there is no comparison with a dense model that has the same computational cost, making it hard to evaluate the sample efficiency of MoE LLMs during continual pre-training. Other continual pre-training methods for MoEs, which are less relevant to our work, mainly concentrate on fine-tuning MoE LLMs with small datasets or expanding MoEs. Our main contribution is identifying relevant MoE architectures for our study, combining them with state-of-the-art continual pre-training techniques, and providing clear guidelines based on our empirical findings. For our study, we selected a dense baseline model, which is a 60-layer, 570 million parameter decoder-only transformer based on the Llama 3 architecture, using JELU activations and the Llama 3 tokenizer. We also included granular MoEs, inspired by the success of DeepSeek MoEs, which activate multiple granular experts along with a shared expert. Each granular MoE has a total of 61 routed experts, 62 active experts, and 63 shared experts, following the same Llama 3 architecture as the dense model. The experts in this model are GEGLU feed-forward networks, sized at 2/3 of the dense model's experts. We trained 2 granular MoEs using different routing algorithms, penalty-balanced and synchron-balanced, without dropping tokens. We also examined switch MoEs, which use full-sized feed-forward networks without a shared expert. Each switch MoE has 65 routed experts, 66 active experts, and follows the same Llama 3 architecture as the dense model, with experts of the same size as the dense model's feed-forward networks, again without dropping tokens. For our continual pre-training strategy, we utilized 3 datasets: Fine Web, the Stack, and German Common Crawl. We initially pre-trained all models on Fine Web for 12 billion tokens to simulate the large-scale web-scraped English data used in many models. We then continually pre-trained these models on 28 billion tokens of code or German data, using specific learning rate schedules and replay techniques to reduce forgetting. We opted for a large amount of replay for full continual pre-training, as seen in previous state-of-the-art work, while also examining the impact of varying the replay percentage. We chose to shift distributions to multilingual and code data, as these represent significant changes from the English pre-training data while remaining realistic. In terms of training details, all models in our study, except for retraining baselines, were pre-trained for 68 gradient descent steps, using a batch size of 69 and a sequence length of 70, with the Atom W optimizer and a cosine learning rate schedule. For continual pre-training, each model followed a cosine schedule starting from a non-decayed checkpoint, while some models in the ablation section were continually pre-trained from decayed checkpoints. We continued training for 71 gradient descent steps, maintaining the same batch size and sequence length as during pre-training. Each model was trained across 72 A100 GPUs using data parallelism. To speed up the forward pass for the MoEs without dropping tokens, we employed the Megablocks kernel. Section Summary. In this section, we explore the large-scale continual pre-training of mixture of experts, MoE, language models, highlighting the limited existing research and our methodological contributions, which include selecting relevant architectures and combining them with state-of-the-art continual pre-training techniques. We detail our training strategy using specific datasets and configurations, aiming to assess the sample efficiency of MoE models compared to dense models while addressing challenges like mitigating forgetting during continual pre-training. Section: Maximum Routing Imbalance, a proxy for latency in MoEs. In this section, we discuss maximum routing imbalance, MRI, as a measure of latency in mixture of experts, MoE, models. While performance is crucial for handling distribution shifts, ensuring a balanced load across experts is equally important. If the load is unbalanced, MoE transformers using expert parallelism without dropping tokens may be limited by the speed of a single accelerator that processes all tokens. This can lead to underutilization of hardware, reduced throughput, and increased costs. To evaluate how distribution shifts affect load balance, we define MRI as the highest proportion of tokens assigned to one expert in a specific MoE layer. Specifically, MRI at a certain training iteration and MoE layer is determined by the total tokens in a batch, an indicator function, the number of routed experts, and the number of active experts. Since latency grows with computation, and the load on a device in a MoE layer increases with the number of experts it handles, we see that MRI reflects the worst-case latency for that layer under a given distribution. We will use MRI in the following sections to analyze how algorithmic changes during continual pre-training impact routing imbalance. Next, we examine the replay percentage used in continual pre-training and consider 2 different checkpoints: one that was decayed during pre-training and another that followed an infinite learning rate schedule without decay. Models in the first group undergo a linear warm-up and cosine decay schedule, while those in the second group start from a higher learning rate and follow an infinite schedule. We report the validation loss for these models during the first 50 billion tokens of continual pre-training. Although we only show the initial 50 billion tokens due to resource limits, the schedules were set to decay at 28 billion tokens, simulating the beginning of a longer pre-training phase. We find that increasing the replay percentage reduces forgetting, as indicated by fine web validation loss, but negatively impacts adaptation to the downstream dataset. Notably, using non-decayed checkpoints consistently improves forgetting without sacrificing adaptation across all replay values. We also analyze routing imbalance by reporting median MRI across all transformer blocks of two types of MoEs during continual pre-training with different replay percentages. We observe that one type of MoE remains robust to distribution shifts, showing only a slight increase in MRI regardless of replay percentage or checkpoint type. This robustness is likely due to a balancing step in the routing process. In contrast, the other type of MoE experiences a temporary spike in routing imbalance after the distribution shift, but it quickly recovers to balanced levels within a short training period. We note that while one type of MoE is more resilient to distribution shifts, this robustness may limit the achievable MRI and could explain the poorer validation loss performance. However, the temporary imbalance in the other type of MoE does not last long enough to hinder its strong overall performance. Section Summary. In this section, we introduce the maximum routing imbalance, MRI, as a measure of load balance in MoE models, highlighting its impact on latency and throughput. We also analyze the effects of replay percentage and checkpoint strategies during continual pre-training, finding that while SBT1 MoEs show robustness to distribution shifts, PBT1 MoEs experience temporary routing imbalances that quickly resolve, suggesting a trade-off between robustness and performance. Section: Language Modeling Performance. In this section, we quantitatively assess the effectiveness of replay and infinite learning rate schedules for continually pre-training our mixture of experts, MoEs. We pre-train our MoEs on 28 billion tokens of code and German Common Crawl data and compare their performance against two baselines: a dense model matched for computational cost and a fully retrained granular MoE baseline, which performs the best in our study. We evaluate performance using various metrics, including validation loss on pre-training and captain datasets, as well as benchmarks for English, German, and code tasks. Our findings show that all MoEs outperform the dense baseline during both pre-training and captain. Among the MoEs, the PBT1 granular MoEs consistently perform better than the SBT1 MoEs, and granular MoEs outperform switch MoEs. This aligns with existing literature, but we believe this is the first instance showing SBT1 routing underperforming compared to PBT1 routing. Since the PBT1 granular MoE achieves the highest performance, we use it as our full retraining baseline. When comparing granular captain MoEs to full retraining, we notice that while granular MoEs have higher validation loss on fine web, they achieve lower downstream validation loss with a similar average. Similar trends are observed when comparing the dense baseline to its full retraining counterpart, indicating that MoEs have comparable continual learning abilities to dense models while benefiting from better sample efficiency. For English evaluation, we find that models trained solely on fine web outperform all others, including full retraining baselines. Granular MoEs exceed switch MoEs, and captain models trained on stack perform similarly to those trained on German. The results are nearly identical when comparing captain models to full retraining, and the dense baseline matches its full retraining counterpart, suggesting similar continual learning capabilities. In the German evaluation, our German-trained models outperform those trained only in English, and among MoEs, those using the same training tokens perform similarly. The difference in accuracy between captain MoEs and the full retraining baseline is minimal, with no clear winner. The dense baseline also shows comparable performance to full retraining, indicating that MoEs maintain strong continual learning abilities in German evaluations. For code evaluation, we see that our models excel in Python code generation tasks, with stack-trained models achieving significant accuracy, while English-trained models struggle. Interestingly, captain switch MoEs slightly outperform their granular counterparts. All captain MoEs perform marginally better than full retraining, and the captain dense model exceeds its baseline significantly, likely due to evaluation noise and training variance. We also analyze routing imbalance during and after continual pre-training. Our results show that granular MoEs maintain lower and more stable routing imbalance compared to synchron balanced MoEs. Continual pre-training leads to only a slight increase in routing imbalance, and we observe that German-trained MoEs exhibit higher routing imbalance on fine web than stack-trained ones. This suggests potential routing interference between datasets. Overall, we conclude that MoEs continually pre-trained with replay and infinite learning rate schedules can match the performance of a full retraining baseline, demonstrating similar continual pre-training abilities to a dense baseline without negative impacts on inference latency or routing imbalance. Section Summary. In this section, we quantitatively verify that continually pre-training mixture of experts, MoEs, using replay and infinite learning rate schedules outperforms a flop-matched dense baseline across various tasks, demonstrating comparable continual learning abilities and improved sample efficiency. Our findings indicate that granular MoEs consistently achieve better performance than switch MoEs, and that continual pre-training does not negatively impact routing imbalance, suggesting robust performance across different datasets. Section: Analyzing changes in routing behavior due to Captain. In this section, we analyze how routing behavior changes due to continual pre-training. We record the routing decisions of the MoE checkpoints before and after continual pre-training using 99 tokens from held-out test data from fine web, stack, and German. Our aim is to see how these decisions evolve from the pre-trained to the continually pre-trained checkpoints. To do this, we adapt three metrics for routing behavior: router saturation, vocabulary specialization, and expert co-activation. We will briefly describe each metric, with formal definitions available in the appendix. For router saturation, we measure the percentage of routing decisions at a specific iteration that match those of the final checkpoint. We extend this metric to multiple training phases during continual pre-training. Our findings show that router saturation is lowest in the early layers, peaks at layer 100, and then slightly decreases after layer 101. The German checkpoint with 5 replay consistently shows lower router saturation than the one with 6 replay across all layers. Notably, while all checkpoints adapt well to German, only the no replay checkpoint experiences significant forgetting on fine web. This indicates that adaptation is most significant in layers 103 and 104, with forgetting patterns linked to lower router saturation. For vocabulary specialization, we measure how often a token from a dataset is routed to a specific MoE expert compared to its total occurrences. By mapping each token to the expert that processes it most frequently, we can calculate the average specialization for each expert. Our results indicate that specialization is notably lower in layers 0 to 88 after continual pre-training, while layers 105 show almost no change. The no replay checkpoint has the lowest specialization in layers 0 to 88, which correlates with its weaker performance on fine web, suggesting that excessive shifts in early layers may lead to forgetting. For expert co-activation, we define it as the ratio of times 2 experts are activated together compared to the total activations of one expert. We create co-activation matrices for each expert pair in a layer and measure changes across checkpoints. Our analysis reveals that early layers show the largest changes, particularly at layer 7 for all continual pre-training models, with the no replay variant showing the most significant shifts. Despite all checkpoints adapting well, only the no replay checkpoint experiences substantial forgetting on fine web. In summary, our results across all three metrics indicate that routing decisions change most in the early layers of granular MoE transformers. The no replay baseline shows the most significant changes in forgetting, suggesting that drastic changes in the initial layers may be linked to forgetting.